I've been getting some questions about mathematical induction, so I decided to make a video. Hopefully it'll help you out. Okay, so let's say it's mathematical induction. So this is basically a method of proof. So if you have a statement or a formula and you want to prove that this formula or statement is always true, we use mathematical induction. So these type of statements have to do with natural numbers. So let's talk about natural numbers first. So the set of natural numbers. Okay, so the set of natural numbers are also called the counting numbers. They're whole numbers and basically starts with 1. So 1, 2, 3, 4, and these keep on going forever. So these are called natural numbers, and the symbol is capital N, like that. Okay, so natural numbers. So we want to talk about some properties that we have for natural numbers, and we are going to discuss even numbers and odd numbers. Everybody knows what even numbers are, what odd numbers are, but let's just look at, I guess, each one in more detail. So even numbers, even, everybody knows what they look like. So it's 2, 4, 6, 8, and you get the idea. So we want to discuss the form of an even number, or like the formula if you want. So by definition, an even number is a multiple of 2. Multiple of 2. So basically that means it's 2 times something. So the way we write that is 2 times something, like blank. So if you say 2 times 1, that's 2. 2 times 2, 4. 2 times 3, 6, and you get the idea. So these are multiples of 2. So the form, or like the formula if you want, the form is 2 times some number, let's say n, 2 times n. Now you can use whatever letter you want here, 2 times x, 2 times m, n, whatever you like. But for the most part, we like to use n for these formulas here. So this is what an even number looks like. This guy right here. Okay. Alright, so now let's, I guess, do the same thing with odds. So let's say odds. So let's see, it's 1, 3, 5, 7. You get the idea. So how do we describe odd numbers? So if you compare, if you take an even number, if you take away 1, you get this number. 2 minus 1 is 1. 4 take away 1 is 3. 6 take away 1 is 5. So then this is like saying a multiple of 2 minus 1. Multiple of 2 minus 1. So in this case, the form or the formula is 2n minus 1. So this is what an odd number looks like. Evens, 2 times some number. Odd, 2 times a number, take away 1. Okay, so now let's look at some properties. properties of even numbers and odd numbers. So let's go up a little bit. Okay, that's good. Let's see here. Alright, so let's say properties. Alright, so let's say what would happen if you take an even number plus an even number. So if you have an even plus another even, according to me, you're always going to get an even number. Well, let's test it. I guess, well, something easy, right? 2 plus 2 is 4. Or what about 2 plus 4? 6. Or, I don't know, 4 plus, what do you want? 8. 12. So, works. So this is a property. Now, we want to know, or I guess be more convinced that this property is always going to work. So I'm just giving specific examples, but I want to make sure that this is something that is always going to work. So in that case, we need to use the form. So, or the little formulas. So an even plus an even is even, right? So let's see, if you take an even number, so it's 2 times some number, call it n, plus another number. So by definition, again, even means 2 times something. Since I already used the letter n, use some different letter. Call it m if you want. Okay. Well, notice that you can factor out a 2. Factor out that guy right there. Factor out this guy right there. 2, and then you have n plus m. Now, is this an even number? Well, even means 2 times something, right? Well, guess what? This is 2 times something. So what's inside here doesn't really matter. What matters is that it meets the definition of an even number, which is 2 times something. So yes, this is an even number. So there you go. So this is like a little mini proof of this property. Alright, so I guess we call this number 1. Number 2. What would happen if you take an odd number plus an odd number, right? So let's say an odd plus an odd. According to me, this is supposed to be even. Okay, so I guess let's convince ourselves a little bit with some examples. Alright, let's make more space here. Alright. Okay, so I guess let's take an odd, so maybe 3 plus 5, 8. Yep. 1 plus 7 is also 8. 5. Well, we already used 5. Well, it doesn't matter. 5 plus, let's see, plus 1. 6. So it really doesn't matter. You get the idea. Now let's convince ourselves with the forms, using the forms or the formula of odd numbers. So if you remember, odd number, what is the form or what is the formula for odd number? Well, it was a multiple of 2 minus 1. So in other words, odd is 2n minus 1. So there's an odd plus another odd. So again, we're going to use a different letter, but it has the same form. 2m minus 1. So let's see what would happen here. Well, like terms, negative 1 and negative 1, if you combine those, that's negative 2. And then 2n plus 2m, 2n plus 2m. What can I do here? They're not like terms, so you cannot add them. But you can factor out a 2 from this part. And if you factor out a 2, what do you have? N plus m. Okay, bring down the 2. And guess what happens? You have a 2 here and you have a 2 here, so you can factor out a 2 again. So if you factor out a 2, factor out that guy, factor out that guy, what are you going to have? Factor out the 2. So you have this, n plus m. If you factor out a 2, well, you're going to think, well, there's nothing there. Well, there's always something there. There's always a 1. So this is like minus 1. And if you want to convince yourself that you did it correctly, the opposite of factoring is to multiply. So if you multiply, it's supposed to give you back the same thing, right? So 2 times n plus m is this part. 2 times a negative 1 is negative 2. Yep, is that part. So far, so good. Now, what we have left here, is this an even number? Well, what does even mean? Even means 2 times something. Doesn't matter what this something here is, even though it looks weird. This is 2 times a number. So guess what? Yes, this is a multiple of 2, so this is an even. So there you go. If you take an odd plus an odd, the answer is always going to be odd. So you get the idea of what these little proofs involve. They're not very easy at the beginning if you're not used to this, because you're working with expressions, not just specific numbers. So this is just to to start getting comfortable with what we're gonna have to do. Okay, so one more. I'm not gonna prove it this time. I'm just gonna give it to you. We could do it the same way, but now that you kind of get the idea, we're not gonna actually go all the way. So the next property, I'm gonna call it number 3. If you have an even number, if you add this with an odd number, the answer is gonna be odd, always odd. Okay, so maybe like 2 plus 3 is 5. Odd. Okay. All right. So we have these 3 properties that we're gonna be using. So far we haven't talked about induction because we need to get the idea first. All right. So there we go. Definition is definition of proposition. So definition. Okay. So a proposition is a statement that is true or false. So a proposition is a statement that is true or false. So proposition is very specific. It's either one or the other. There's nothing like in between. True or false. Now, since we're talking about induction, all the statements that we're going to be talking about have to do with natural numbers. So this is where notation comes in. You're going to see that most books use this type of notation, like S and then a little n, subscript. So Sn is a statement about natural numbers. A statement about natural numbers. Oh, let's see, I'm not that good at using this pen here. Let me try it again. Natural numbers. Alright. So for this, you're not going to be working with, like if you have a formula, a statement, you're going to be plugging in natural numbers. In other words, whole numbers. You're not going to be plugging in fractions, decimals, or nothing weird like that. Natural numbers. Alright, so let's take an example. Let's see. So let's see, Sn, this is my statement. So my statement is that if I have this expression, n squared minus n plus 5, this is always going to give me a prime number. So n squared minus n plus 5 is prime for all n greater than or equal to 1. This part is very important here. So maybe choose a different color. So this guy right here. This is telling you the numbers that you're going to be using or testing this formula to see if it works or not. So I'm interested only in numbers that are beginning with 1. So if you notice, we're not going to be testing negative numbers. So starting with positive, 1, and so forth. So if I start plugging in these numbers here, I'm supposed to be getting prime numbers. So is this always going to be true? So we have to test if this statement is true or false. So true or false. Okay, so let's test it out. Let's see what's gonna happen here. So I guess let's test, well, the first number on the list starting with 1, and then let's see what happens. So using this notation, if I write S1, that means you're gonna test it when n equals 1. So when n equals 1, in other words, you're gonna plug it in. What do we get? 1 squared minus 1 plus 5. 1 minus 1 cancels out. Plus 5, so 0 plus 5, right? So this is 5. Is that a prime number? Yes, it is. If you remember, prime numbers are numbers whose only factors are 1 in itself. So you cannot factor this number with other numbers. The only numbers that factor into 5 are 1 times 5, 1 and itself. So guess what? This guy is prime. So far so good. It worked. And then if I say S2, that means plug in a 2, right? Alright, let's see what's going to happen here. So if I go 2 square minus 2 plus 5, what is this? This is 4. 4 take away 2 is 2. 2 plus 5, that's 7. Yep, 7 is prime because the only numbers that are going into 7 are 1 in itself. 1 times 7. This guy is prime. Yep. So if you look at it, so far so good. So let's make more room here. So by the way, if we want to show that this is always going to be true, what does that mean? That means that you have to check every single number. And if you think about it, it's not really possible. So that's why we have this method called mathematical induction, because it's not possible to check every single number because there's infinitely many numbers. Okay, so what we're doing here is we're checking just to take examples so we can get an idea what's going on, but obviously we can't check all of them. Okay, so I guess let's do just a few more. Let's check 3. We left off at 3. So does it still work for 3? Let's see. 3 squared, take away 3 plus 5. Let's see, 9, take away 3. What is that? 6. 6 plus 5 is 11. Yep, this is also prime. Let's see, I guess 4. Okay, so if we're using 4 plug in a 4. Let's see what happens. 4 squared, take away 4 plus 5. How much is this? 16. Take away 4. What is that, like 12? 12 plus 5 is 17. Well, are you convinced yet? Because it looks like it's working. Let's try another one. One more. Let's see what's up. So if we go 5. So 5 squared. Take away 5 plus 5. What happens here? 25 minus 5 is 20. 20 plus 5 is 25. Is this prime? It's not, because this one you can't factor. It factors as 5 times 5. So it's not prime. So doesn't work. So this is a good example. Just because it looks like it's working doesn't mean it always will work. Even if you were to take 100 examples, a million examples, and if they all work, doesn't mean that it's always gonna work. So that's why we need something that's gonna help us with this, something that is gonna prove that it's always gonna work, because it's not possible to check manually. So doesn't work. So this statement is false. In order for a statement to be true, it's always supposed to be true. So that's the idea. Alright, so let's try another one. Actually, I think we get the idea. So now let's jump into induction. So let's say getting the idea of how induction works. Okay. So let's say let's set it up this way. What numbers are in S if we have the following properties? Okay, so number 1. So let's say that we know that for sure. So I'll put S here. And we're gonna start putting the numbers that go inside of S. Okay, so let's say that we are told that 5 is in my set here. Okay, 5 is in here. So 5 belongs, that's what this little symbol means. Okay, 5 belongs or is in the set S. Okay, let's say that we also know the following. If K is in S, then K plus 1, and I put this in parentheses so we know that this is supposed to be together, is also in S. So here we're using a variable, right? So here K is any number. Okay, it's arbitrary. So this is a good word here that we need to use. Maybe I'll choose a different color here to emphasize. When you see K, this means arbitrary. Arbitrary. Okay. Okay, so how does this work? So if you're talking about a number K, and you compare it to the number k plus 1, k plus 1 is a number that comes after k. In other words, k is before k plus 1. So what this is saying is these have to come together. So whenever you have a number like 5, automatically, according to this property, you need to also include the number that comes after it, k plus 1. So if you have 5, automatically you need to include 6. Okay, but what's going to happen there? Now you have 6. So if you have 6, the number that comes after 6 also has to be included. That's the rule here. So that means if you have 5, 6 has to come here. If you have 6, 7 has to be here. If you have 7, 7 has to be here. So I don't know if you see the pattern here. When you put these two properties together, we can start filling out what goes in here. So for sure 5 is in here. But because 5 is in here, automatically the number after it has to be also in there, 6. But because 6 is here, automatically the number after 6 has to also be in there, 7. But because you have 7, who also has to be there? 8, 9, 10. So then you notice that automatically the rest are also going to be in here. And that's the idea of induction. If you can understand this, then you understand what induction is doing or how it works. Okay, so we think of this, or I guess a very popular example to show this is the domino effect. So this is a nice little picture that almost everybody likes to use. So if you have some dominoes here, well, they're standing up, right? Like this. 1, 2, 3, 4. 1, 2, 3, 4. We're supposed to start with 5 here, so this is the 5th one. So this is like the 5th one. Well, let's put some more. And you have a bunch of them, right? So if you tip over the 5th one, right? So if you take this one, push it, so it tips over, then this is going to push over, tip over the one in front of it. This guy tips over this one, tips over this one, tips over this one. So guess what happens? Well, I made a mistake here. It starts here, so that's the 4th one. Let me erase that one. Okay, so starting with the 5th one, if you tip over the 5th one, the rest fall. So then it's automatic, right? So it's basically what's going here. If you know that you have 5, then automatically, once you know you have 5, 6 has to be in there. But if 6 is in there, automatically 7 is there, 8 is there, 9 is there, and so on and so forth. Okay? Well, that's the idea. Let's make more space. Okay, so now let's give the like the formal definition. So that's the idea of induction. Now let's give the formal definition of mathematical induction. Okay, so I guess let's say definition, and it's called principle of mathematical induction. Okay, it's a lot of writing, so I call it PMI. PMI. So we're, like we said, we're basically checking these formulas and seeing if these formulas work and if they always work, right? So going back to the notation, Sn. So Sn is a statement that will be true, that will be true for all the numbers. In other words, for n greater than or equal to 1, provided the following conditions are satisfied. So provided we have the following conditions. Okay, so we need to have two conditions. Number one, S1 is true. So what does this mean? If you test the formula by plugging in the first number, it has to work. It has to be true. Number two, this is also called like the inductive step. If Sk is true, then Sk plus 1 is true. So this is basically what we just did at the beginning. Instead of using numbers, I'm using statements. So what does this mean? We have, if we put these together, S1 is true, but because you have 1, automatically the number that comes after 1 has to be in there. So S2 is going to work, but if 2 works, automatically the number that comes after 2, that also works. 3. But if 3 works, who also has to work? 4. So then, which numbers work? Well, all of them, from 1 all the way to infinity. In other words, they all work. Okay, so that's why it's always gonna work, or it's always gonna be true for n greater than or equal to 1. So that's the idea behind mathematical induction. Okay, so for the most part, most of these, they start with 1, but in general, you can start wherever you like. You can start with 1, like the one I did before this, I started with 5. So depending what the statement looks like, depending on what they're asking you to prove, they'll tell you what you're supposed to check, whether it's starting with 1, with 5, with 10, or whatever. So this is not something you worry about, because they tell you what you're supposed to be proving and where you're supposed to be starting. Alright, so let's keep going here. Okay, let's see. Okay, so now that we have the idea, we need to know how to write it. You know, how it is that you're supposed to be writing this proof, and that's part of the confusing part as well. I get the idea, but how is it that I'm supposed to be writing these? Like, what are the steps? So I guess I'll call this the outline. How do I set it up? How do I write it? So the outline. In other words, every time you're doing one of these proofs, this is the way you're supposed to set it up, right? So this is the outline. So they have to give you something. So to begin with, what is it that they give you? They give you the statement, right? So given, they give you this some formula that you need to check or prove. So here goes the statement. Statement or formula. And then they need to tell you when it works, or the condition when it's true, right? So n greater than or equal to some number here. So they have to tell you what this is, right? So this is when it's true, whether start with the number 1, the number 5, or the number whatever. So now let's see. Okay, so they give you this. Now how do we set it up? So let's say how to write it. How to write. In other words, the steps we're gonna use. And number 1, I'm gonna write them like with numbers to make it easy. So this is all sometimes called the base case. What you start off with, base case. What is the first thing you're gonna test to see if it works? Okay, that's what the base case means. So in this, you're gonna test that it's true or test if it's true. Erase. Test if it's true for the first number, whatever number they tell you to begin with. This is where you check it. And you can check as many as you like. And a lot of times it's a good idea. You have this weird looking formula and you're supposed to be proving it, and you don't really know what this formula does or how it works. So I would say test as many as you want, but in reality you're only required to do just one. Number 2, assume Sk is true for arbitrary k. This is where I said k, if it's arbitrary, it means it could be any number. It's not a specific number, it's any number that you can just plug in to the formula. And then number 3. So I know this sounds kind of weird, but when we do it, it'll make more sense. Number 3, use Sk to establish Sk plus 1. Okay, so yeah, all of this stuff sounds pretty weird, kind of complicated, but it goes back to the examples that we did on the previous page. So this is just a matter of, it's not a different idea, it's the same idea. This has to do with how we're supposed to write it. And that's what's confusing with this is, the writing part. We understand the idea behind it. Now we need to know how to write it out. Okay, so let's do an example all the way. So example number 1. Okay, so they're gonna give you a statement. The statement is the following: n squared plus n is even for all n greater than or equal to 1. This is a formula. These are the numbers that work with this formula, and it's supposed to work for all of them. So this is what we have to show. So step 1 is to test it, right? So you test the first number on the list, starting with 1, S1. Okay, so if you plug in a 1, the answer when you work it out is supposed to be an even number. Well, let's see. Plug in a 1. So 1 squared plus 1 equals 2. Is that even? Yes, it is. It works. So like I said, you only need 1 to check the first number, but it's not a bad idea at the beginning, to use several examples, maybe to just convince yourself first. What happens if I plug in a 2, right? 2 squared plus 1. Let's see. 4 plus 1. I'm messing up here. This is 2, so this is supposed to be a 2. There we go. And there we go. So n squared plus n. So you plug in a 2 there, plug in a 2 there. 4 plus 2 is 6. Yep. One more. 3. So 3 squared plus 3. So what is this? 9, 10, 11, 12. 12. There you go. Alright, so it looks pretty convincing so far. So now let's do the next step, number 2. So for step number 2, what I want you to think is you're just gonna switch from n to k. So you're just gonna switch from n to k. So this is what step 2 is. So when you hear this fancy assume sk is true, in this step what you're gonna do is you're gonna switch from n to k. So what does it look like? So then switching the k's, you have k squared plus k is even. Remember here that k is arbitrary, right? So these are specific k's. 1, 2, 3. So it works with the number 1, works with the number 2, works with the number 3. Here when we swap out a k, that means k could be any number. It could be 5, it could be 10. And we're checking that if 10 works, then automatically the number after 10 works. 11 works. Okay. But if 11 works, automatically the number that comes after 11, that has to work. 12. So if 12 works, 13 works. If 13 works, 14 works, so on and so forth, right? So what we're basically saying is that we have to use sk to show that sk plus 1 is even, right? So if it works for 5, then it works for 6. So that means if you plug in a 5, the answer is supposed to be even. And if you plug in a 6, the answer that comes out is supposed to be even. And if you plug in a 7, the answer that comes out is supposed to be even. That's because, like I said here, if sk is true, then the number that comes after it, that also has to work with the formula. So that's what we're going to try to do. Okay. So we know what sk means. basically we just change the letter from N to K right here. But what does this guy look like? SK plus 1. Well, it's basically the same thing. In place of N, you replace whatever you have here. So then there we go. Here we go. So whatever you have here, you're gonna plug in into your formula. There and there. So if you plug in a K here, K goes here, K goes here. Well, if you look at it, down here we have K plus 1 now. So you take out N, what do you put there? K plus 1. What do you put there? K plus 1. What do you put there? K plus 1. And if we do that, what do we get? Well, let's make more space. Okay, so then let me put it back. So what does SK plus 1 look like? SK plus 1. If you plug in a K plus 1 there, what does it look like? Well, you need parentheses, right? K plus 1. Plug in K plus 1. What does that look like? Plus K plus 1. Okay. And this new formula is supposed to be even. Okay. So we're supposed to use this formula in blue to show that this new formula, let's say I'll put it in green. So we're using the blue formula to show that the green formula also works. So in other words, this blue formula means that this answer will be even. This green formula means that this answer will be even. You have to use the blue one to establish the green one. So that's always how induction works. Okay, you have to use SK to make SK plus 1 work. Once you do that, you're done. That's exactly what we're trying to do. Okay, so in other words, this SK plus 1, this is the goal. Once we get this part, we're done. So if you want, I'll call it our goal. There we go. All right. Now let's make more room here. Okay, so now let's do some algebra. Okay, let's see here. So I guess here, this is FOIL, right? K plus 1 multiplied with K plus 1 plus K plus 1, right? FOIL this out. K times K, that's K squared. K times 1 is K. 1 times K is another K. 1 times 1 is 1. Bring down this. Now what can we put together? This is the only thing that has K squared, so bring that. How many K's we have? 1, 2, 3. Like terms, this one with that one is another 2 altogether. Okay, now let's see. Okay, this is a tricky part. I think this is where I got ahead of myself. You need to use SK to establish SK plus 1. So here we go. Let me bring it back so we can see. There we go. Okay, so you're supposed to use this part to get this part, right? So this part, you're gonna see that you have k squared plus k together. So you need to have these together when you're working this out. So this is where I got ahead of myself. So let me see, let's, whoops, eraser, erase, okay. So that means we have to look for these two together. Do we have those? Yep, we have them right here. So it is this part right here. Yep. So now that we have those together, leave that alone. These are the ones that you're supposed to add. So then those, k plus k is 2k. 2k plus 2. There we go. So k squared plus k, according to the formula, this is going to give you an even number, right? Okay, so this is even right there. Now what about this guy? What type of number is this? Well, what we're hoping for is, if you remember, we have a property, an even plus an even, the answer is even. And if that's what we get, we're done because that's the goal. Well, let's see if we can make this work. You can factor out a 2, right? This is where the magic happens. What does it mean to be even? Even means 2 times something. Doesn't matter what this something is. That's exactly what we have here. So guess what? This guy is even. So then, in other words, we have an even plus an even. That means we have an even. And that's exactly what we're trying to get. This formula, using this formula, in other words, the green formula, using the blue formula, we were able to show that the green formula is true. It's true that it's even because that's what we have here. Even plus even is even. And we're done. So it's true statement. So you're using SK to show that SK plus 1 is even. And I know it's a little tricky, but that's the way it works. So that means that this is going to take practice. So I'm going to do another one for you. Okay, so just to recap, it's going to be always these 2 steps. Step 1 means you plug in numbers into the formula to see if the formula works or not. How many do you need to plug in? Just one, the first one. But I encourage you to plug in as many as you want so you can see what's going on first. And then step 2 is you take your formula and you replace n with k. And then you take your formula and you replace n with what? K plus 1. So you have these 2 new formulas, one with k, one with k plus 1. And this is where the tricky part is. You have to use the first formula, the one with k, use this to establish this formula over here. So somehow, this is where the tricky part is, you have to use this to make this guy work. And that takes practice. So let me do another one. Okay, so number 2 or example 2. Let's see here. Example number 2. Let's see. Okay, I know which one. I'll do the one that everybody does. Every book does this one. Sn. So you have 1 plus 2 plus 3 plus 4 plus 5 plus n equals n plus 1 over 2 for all n greater than or equal to 1. All right. So what does this mean, or how does this formula work? Well, basically what we're doing is we're adding natural numbers. And if you think about it, it looks pretty easy. But what if you have a bunch of natural numbers? Let's say you have 100 of these. So let's say if you have 100, what does that mean? Well, that means you're going to take the number 1 plus the number 2 plus the number 3 plus the number 4 plus the number 5 plus 99 plus 100. Well, that would take you a while. You would use your calculator. But we have a formula that would give you this answer without having to do all of this, right? So according to this formula, you would plug in 100 in place of n. So it's 100 plus 1 divided by 2. So 100 divided by 2, that's going to be 50 times 101. All right. And then if you do this calculation here, that's supposed to give you the answer for all of this. Okay? That's supposed to give you the answer, right? Now, does this work or not? That's what we're trying to show. Okay? It does work, because I know it works already. So, but it's our job here to prove it. Okay? So let's set it up, right? So we were doing it in steps. So step number 1, right? You test the first number, see if it's true, right? S1. Okay? So S1 means you plug in a 1. So in this case, that means you're adding the first number. Well, that means 1 by itself. You're adding just one number. And that's supposed to be equal to, on this side, if you plug in a 1, what do we get? So let's see, 1, plug in a 1, 1 plus 1, that's 2. 1 plus 1 divided by 2. So on this side you have a 1. 1 times 2 over 2. Guess what? The 2's cancel. 1 equals 1. Is that true? Yes, it is. True. Okay, so it works for the first number. Now let's try the next one, because remember we said all we need to do is test the first number. Let's see what's going on here. There we go. Make more space. But it's a good idea to test several examples, so let's try more. Let's see. 2. So what does this mean? The first two numbers, the first two natural numbers, so 1 plus 2. And the formula is, so I don't want to go back and forth, so the formula was n plus 1 over 2, right? So then here you plug in a 2 there and a 2 there. So it's 2 plus 1 over 2. So this is 3. Cancel those. What is that? 3. Yep. Works. Now let's do another one. So now you're adding the first 3 numbers, the first 3 natural numbers. 1 plus 2 plus 3. And then you plug in a 3 into the formula. So plug in a 3 there, plug in a 3 there. So let's see what happens. 3 plus 1 over 2. So let's add all of this. 1 plus 2 is 3. 3 plus 3 is 6. Let's see what happens over here. Well, that's a 4. 4 divided by 2. So if you cancel this, this is gonna be 2 goes into 4 2 times. 3 times 2 is 6. 6 equals to 6. Yes, it is. True. All right. So now I see how the formula works. So I'm gonna go ahead and do the next step. So like I said, you don't need to do all of this. You can just do the first one. But I like to do several examples so I can see how the formula works, because otherwise I'm trying to prove something and maybe I don't even understand how it even works. Alright, so let's see, more space here. So that was step one. Okay, let's see. Come on, buddy. Need to make more space here. Alright. Okay, so well, that's good enough. So as you can see, I don't have a lot of practice doing this. Alright, so we were doing step two. Okay, step two. Okay, so to do the step two, this is where we're going to use sk and sk plus 1. So for step two, I said when we write, assume let's see what I don't know what happened there. Assume sk is true. So what we're saying here is in the formula, instead of n, you put a k. So everywhere you had a n, you replace it with k. So let me remind you what the formula looked like with n. So it was 1, 2, 3, 4, 5. You get the idea. Up to some number, n plus 1 over 2. So now, if you put a k there, what does it look like? So sk 1, 2, 3, 4, 5, k plus 1 over 2. So now we have to use sk, to show that sk plus 1 is true. Right? So now what does sk plus 1 look like? Well, wherever you see an n, you plug in k plus 1 this time, right? So, well, how does that look like? 1, 2, 3, 4, 5. Right there, plug in. So, right there, plug in k plus 1, plug in, plug in. So what does it look like here? So right there, you're going to put k plus 1. You don't have to put parentheses, but I'll put parentheses. K plus 1 right there. K plus 1. And then you have another one right there. So if I put k plus 1 plus another one, that's k plus 2, right? Over 2. Okay, so then now we're working with the two formulas, right? We said the blue formula, you use it to show that the green formula works. Okay, so use this to get this one. In other words, this is what we have to end up with. This is the goal. Once you get this part using this part, we're done. So that means we're gonna do some algebra, and this is the tricky part. So okay, let's see what we're gonna do. Okay, so if you notice, this is an equation. So when you have an equation, you have two sides of an equation, right? Left hand side, right hand side. So let's I guess, do I have red maybe? See what this is. Left hand side. This is right hand side. You start with one side of the equation, you have to end up with the other side of the equation. That's what we're gonna do. Well, let's start with this left hand side. So 1, 2, 3, 4, 5, all the way up to, well, this is where the trick is. Before I keep on writing, you're supposed to use the blue box to get the green box, right? But if you look at the blue box, when you're adding these numbers on the left hand side, 1, 2, 3, 4, 5, it goes up to k. It doesn't go up to k plus 1. So then on this side of the equation, this goes up to k plus 1. So in other words, what is a number that is before k plus 1? Well, what is a number that is before 2? 1. What is a number that is before 3? 2. So that means the difference here is 1, right? So if this is 5, what is the number in front of 5? 4. So if this is k plus 1, who is in front of k plus 1? Well, take away 1 from it, just k by itself. So that means I can put k, because that's before who? K plus 1. Alright, so now that I have this left hand side is exactly the same as this left hand side right here, the only thing I did is I wrote it putting that number that wasn't there, that wasn't written. It was there, but I just didn't write it. But why did I write it? The reason that I write it is because I have to use the blue box. And according to this blue box, the numbers from 1 all the way up to k can be replaced according to this formula with k plus 1 over 2. In other words, from here to here, according to my formula, it's k plus 1 over 2. This is k plus 1 over 2. Bring down k plus 1. Okay, so here is where I can start to visualize what I'm supposed to do. I need to make the left hand side equal to the right hand side. So in other words, I need to do algebra to make this exactly this part right here. K plus 1, k plus 2 divided by 2. Well, if you notice, this is a fraction. I have a fraction here, I don't have a fraction here, so I need to make this a fraction. In other words, to get a common denominator. So, if I make this into a fraction, this is over 1. Common denominator is 2, so what do? You multiply times 2 there, multiply times 2 there. Well, let's work this out. If I multiply this and put it over 2, because they both have a 2 on the bottom now, so I can just write it one time. Then I can multiply this out, right? K times k is k squared. K times 1 is just k. 2 times k, 2 times 1, more space. Okay, let's see, keep on going. You can add these, right? 1k and 2k is 3k. K squared plus 3k plus 2 over 2 guess what? The numerator factors. So going back to our algebra days, how do we factor? Well, the two numbers in the front give you the first number. K times K gives you K squared. The two numbers in the back, when you multiply, give you the last number, right? So if that's the case, what do we need? Well, what if I put 1 and a 2? Does that work? Let's see. 1 times 2 is 2. Yes. And then what about this middle number? Well, the way it works is two numbers, then when you multiply, give you the last number, and when you add them, gives you the middle number. 1 times 2 is 2. 1 plus 2 is 3. Yep, it works. Well, what did we end up with? Well, remember that we started on the left-hand side? We were supposed to make it look like the right-hand side. Did we do that? Yes, we did. This is the right-hand side. Let's go back. The goal was to have k plus 1, k plus 2 over 2, k plus 1, k plus 2 over 2, and that's exactly what we needed. Okay, so guess what? We're done. So I guess if you want to finish this off, I guess officially, right? Because we want to write it the right way. Once you do this, you say, I didn't do this in the previous problem, but I guess to make it official, you could. Therefore, Sn is true for all n greater than or equal to 1. This is called the conclusion. The conclusion. So in other words, because we use the steps, step 1 and step 2, that shows that the original statement works. So let's go back to see what we did. So remember, this was the statement that was given, the formula that I'm supposed to prove. If you add numbers from 1 all the way up to n, it equals n times 1 over 2. When does it work? For all numbers starting with 1. Okay, and the step 1 is test if it works for the first number. That's what we did here, and it does work. And you can test more examples if you want, just so you can see how the formula works. You only need the first one. So this is step 1. Test it out first. Step 2 is where you start working with the formulas. Step 2 is where you say assume Sk is true, and basically the only thing you're going to do is in the original formula, wherever you see n, you're going to plug in a k. That's what we did here, which gives you this new formula with k now. And then the next step is to say that you're going to use this new formula to show that Sk plus 1 is true. So Sk plus 1 works the same way. That means that you plug it in into the original. Wherever you see n, you put k plus 1. So you put it there and there. And that's where we get this new formula. So we have this blue one and the green one. The green one is the goal. So to get our goal, you use the blue box to get the green box. And you're going to use some sort of algebra. So in an equation, we have two sides, left-hand side, right-hand side. So I start with the left-hand side, and I'm supposed to get the right-hand side. So I started with the left-hand side, which is this part right here. And then I noticed that I'm adding a bunch of numbers. I'm going up to k plus 1. So then I said, well, let's think about it. What is the number that is in front of k plus 1? What is the pattern? Well, if you have 3, what is the number in front of 3? 2. If you have 2, what is the number in front of 2? 1. So it's 1 less than it, right? So if this is k plus 1, who is in front of k plus 1? K. So let's rewrite it. 1, 2, 3, 4, 5, k plus 1 because k is in front of k plus 1. Why did I do that? Because you have to use the blue box to get the green box, and the blue box goes all the way up to k. So then I said, oh, I have the part that I needed. So from 1 to k, it's the blue box formula, which says you can replace it with k plus 1 over 2. So then up to here, according to my blue formula, k plus 1 over 2 plus the k plus 1 that was there. And remember that my goal is to get the right hand side, k plus 1, k plus 2 over 2. Well, if that's my goal, that means I need a fraction. So then this was a fraction from the formula. This wasn't a fraction, so I made it into a fraction. How? Putting it over 1. But common denominator is going to be 2, so you multiply 2 and 2. So now the 2 is in the denominator. Multiply this out, gives you this expression. Combine like terms, k squared plus 3k plus 2. This factors k plus 1, k plus 2 over 2, and that's exactly what I was supposed to get. That was the goal. So we used the blue box to get the green box. So that means we're officially done. We got the right hand side. And then if you want to make it official, I guess, the way you write it, therefore, the formula that we started off with has been proved. Therefore, Sn is true for all n greater than or equal to 1. So that is basically the idea of mathematical induction. It's not very easy at the beginning, especially. So mathematical induction is just basically a method of proving a statement, a formula. And when is this used? Well, since it's not possible to test every single number by plugging in, you plug in a 1, plug in a 2, plug in a 3, plug in a 4, and it looks like it's always working, but there's infinitely many numbers, so you can't plug in all of them. That's impossible. So you need a way that is going to check for all these numbers automatically, and that's what this method does. Okay, it checks for all the numbers automatically if you use this outline. So it's mathematical induction. If you have any other questions, just let me know.